Welcome to the lecture on integer programming module 2. In this module, we will discuss Gomory's cutting plane method for mixed integer programming problem. We will also discuss branch and bound method. This method is the most general method for solving integer programming problem, because this method can be applied to all integer programming problem as well as mixed integer programming problem. In branch and bound method, the basic idea is to subdivide the feasible region into several parts and then examine the optimal solution for each sub region, and then we have to look for the feasible solution which actually gives the optimal value of the objective function. So, let us now proceed to discuss Gomory's cutting plane method for mixed integer programming problem. In the mixed integer programming problem, some variables are restricted to integers, but not all. So, we first ignore the integer restrictions and then we apply usual simplex method. If we find the integer restricted variables are not integers in the solution obtained by simplex method, then we proceed further to construct Gomory constraint. We choose the largest fraction among those basic variables which are restricted to integers. Let it be f k 0, then the fractional cut, that is Gomorian constraint, is defined as given below. Minus f k 0 equal to minus summation f k j x j, where j belongs to R plus f k 0 by f k 0 minus 1 summation f k j x j, where j belongs to R minus plus g 1. Here R plus is the set of all j such that f k j is greater than equal to 0, and R minus is the set of all j such that f k j is less than 0, and g 1 is the Gomorian slack. It could be noticed that in this fractional cut, we consider both negative and positive fractions, and if we ignore the negative fractional part, then the Gomorian constraint is same as we have already mentioned for all integer programming problem. Now, we consider the following mixed integer programming problem. Maximize z equal to 4 x 1 plus 6 x 2 plus 2 x 3, subject to 4 x 1 minus 4 x 2 is less than equal to 5, minus x 1 plus 6 x 2 is less than equal to 5, minus x 1 plus x 2 plus x 3 is less than equal to 5, where x 1, x 2, x 3 is greater than equal to 0, and x 1, x 3, these two variables x 1, x 3 are integers, whereas x 2 is free to take any non-negative value. We introduce 3 slack variables x 4, x 5 and x 6, one to each constraint. Then an initial VFS will be x 4 equal to 5, x 5 equal to 5 and x 6 equal to 5. Ignoring the integer restrictions, the LPP can be solved by simplex method, and the final iteration of the simplex table is shown below. As you can see that Zj minus Cj is greater than equal to 0 for all j. Therefore, the optimality condition is satisfied, and from this table we read the optimal solution as x 1 equal to 5 by 2, x 2 equal to 5 by 4 and x 3 equal to 25 by 4. Since x 1 and x 3 are integers, obviously this solution is not acceptable. So, we proceed to find Gomory's constraint. Now, we have maximum of f 10, f 30 equal to maximum of half and 1/4, which is equal to half. Therefore, from the first row of the above table, we have 2 plus half equal to 1 plus 0 into x 1 plus 3 by 10 into x 4 plus 1 by 5 into x 5. The corresponding fractional cut is minus 3 by 10 into x 4 minus 1 by 5 into x 5 plus g 1 equal to minus half. Now, adding this new constraint to the final iteration of the simplex table, we proceed to find the optimal solution by dual simplex method. The slide shows the table or iteration for dual simplex, and since the component of the vector b are all not non-zero, therefore, we proceed to find the departing vector. Here the departing vector is z 1, and we can easily obtain the entering vector as a 4, and then we proceed to the next iteration and see that in the next iteration all the components of b are non-negative, hence the feasibility condition is satisfied, and we can get solution from this table as x 1 equal to 2, x 2 equal to 7 by 6 and x 3 equal to 35 by 6. Since x 3 is not integer, so we have to proceed further, that is we have to construct further another Gomorian constraint. For this, we consider the third row, which can be written as 5 plus 5 by 6 equal to x 3 minus 1 by 6 into x 5 plus x 6 plus 5 by 6 into g 1. Using equation 1, the corresponding fractional cut is given by minus 5 by 6 is equal to minus 5 by 6 into g 1 minus 5 by 6 by 5 by 6 minus 1 whole into minus 1 by 6 into x 5 plus g 2, where g 2 is the second Gomorian slack. And if we simplify it, we get minus 5 by 6 x 5 minus 5 by 6 g 1 plus g 2 equal to minus 5 by 6. One thing is to be noted here, that in constructing the Gomorian constraint here, we consider both negative and positive fractional parts. So, adding this constraint to the last iteration of the above simplex table, we proceed to find the optimal solution by dual simplex method, and this slide shows the iteration in dual simplex method, and clearly the last row, from the last row we see that g 2 is the departing vector, and we can easily calculate the entering vector as a 5, and we proceed further. This slide shows that the feasibility condition in dual simplex method is satisfied, as all the components of B are positive. So, we arrive at the optimal solution of the given IPP. We find that x 1 equal to 2, x 2 equal to 1 and x 3 equal to 6 as the solution of the problem, and the corresponding value of the objective function z max is equal to 26. Now, we proceed to discuss another important method, which is called branch and bound method. Branch and bound method is the most general method for solving integer programming problem, because this method can be applied to all integer programming problem as well as mixed integer programming problem. This method actually partitions or branches the feasible region into subsets and then examines each of them successively until a feasible solution that gives optimal value of the objective function is obtained. We now discuss branch and bound algorithm. Step 1. First, we obtain an optimum solution of the given LP problem, ignoring the integer restrictions. In the next step, we can terminate the iterations if the optimal solution of the LP problem satisfies the integer restrictions. Otherwise, we will go to the next step. Step 3. Considering the value of objective function as upper bound, we obtain the lower bound by rounding off to integral values of the decision variables. Next, let the optimum value x j star of the variable x j be not an integer. Then we subdivide or branch the given LP problem into two subproblems, subproblem 1 and subproblem 2. In subproblem 1, we consider the given LP problem with an additional constraint x j is less than equal to greatest integer content in x j star. In subproblem 2, we consider the given LP problem with an additional constraint x j greater than equal to the greatest integer content in x j star plus 1. In the next step, we solve these two subproblems, and then we may arise three cases. In case 1, if the optimum solutions of these two subproblems are integral, then the required solution is one that gives the largest value of z. Case 2, if the optimum solution of one subproblem is integral, but the other subproblem has no feasible solution, then the required solution is the same as that of the subproblem giving the integer valued solution. Case 3, if the optimum solution of one subproblem is integral while the other is not, then we record the integer valued solution and repeat steps 3 and 4 for the non-integer valued subproblem. In the next step, we repeat steps 3 to 5 until all integer valued solutions are obtained, and finally, we choose the solution amongst these integer valued solution that yields an optimum value of z. I would like to mention one thing here, that if the number of variables is large or if the LP solution to the problem is not optimal, then branch and bound method is not suitable, because the number of iterations required to solve such a problem may be too large. We have so far discussed Gomory's cutting plane method for mixed integer programming problem. We have also discussed branch and bound method for solving integer programming problem, and we have already mentioned that this method, the branch and bound method, is the most general method for solving integer programming problem, as it can be applied to solve both all integer programming problem and mixed integer programming problem. But it has one disadvantage, that if the number of variables is too large, then this method is not suitable. However, if the number of variables is restricted to 2 only, then a graphical method can be applied to find the solution of each subproblem. We now proceed to take some example and see how branch and bound algorithm can be applied to find solution of IPP. Consider the following example: maximize z equal to x1 minus x2 subject to x1 plus 2x2 is less than equal to 4, 6x1 plus 2x2 is less than equal to 9, x1, x2 is greater than equal to 0 and are integers. This problem is an all integer programming problem. Let us solve the given problem by graphical method, as the problem has only 2 variables x1 and x2. The slide shows the feasible region O, A, B and C, and the extreme points of the feasible regions are 0, 0, 3 by 2, 0, 1, 3 by 2 and 0, 2. From the extreme points of the feasible region, we find the optimal solution as x1 equal to 3 by 2 and x2 equal to 0. The corresponding maximum value of z equal to 3 by 2. Since x1 is not an integer, we proceed further. Now, x1 equal to 3 by 2, which implies that 1 is less than x1 star less than 2. So, considering the value of z as initial upper bound, that is z equal to 3 by 2, the lower bound is obtained by rounding off the values of x1 and x2 to the nearest integers, that is x1 equal to 1 and x2 equal to 0. Here the lower bound of z is 1. Now, since the greatest integer contained in x1 is 1, so we branch with the constraints x1 is less than equal to the greatest integer contained in x1 star and x1 is greater than equal to the greatest integer contained in x1 star plus 1. The slide shows 2 subproblems. In the subproblem 1, we have the additional constraint 0 less than equal to x1 less than equal to 1, and in subproblem 2, we have the additional constraint x1 is greater than equal to 2. The optimal solutions to these subproblems can be obtained graphically as shown in this slide. For the subproblem 1, we have the feasible region, and for the subproblem 2, we are not getting any feasible region. Since we are not getting any feasible region for the subproblem 2, so we are getting no feasible solution for the subproblem 2. whereas for the sub problem 1 we are getting the optimal solution from the extreme points as x1 equal to 1 and x2 equal to 0 and the corresponding value of z is equal to 1. Since from these two sub problems we are getting only one solution and which is an integer solution, therefore, the required solution is obtained, which is x1 equal to 1, x2 equal to 0 and max z is equal to 1. Let us consider another example. Minimize z equal to 4x1 plus 3x2 subject to 5x1 plus 3x2 is greater than equal to 30, x1 is less than equal to 4, x2 is less than equal to 6 and x1, x2 greater than equal to 0 and are integers. That means this problem is an all integer programming problem. Let us solve this problem graphically ignoring the integer valued restrictions. The slide shows the feasible region for the problem and from the extreme points of the feasible region we see that the optimal solution is obtained at the point A, that is at the point 4 10 by 3, that means x1 equal to 4 and x2 equal to 10 by 3 and the corresponding minimum value of z equal to 26. Here since x2 is not integer, so we have to proceed further. Since the greatest integer content in x2 star is equal to 3, we branch the variable x2 and the branches will be like this: x2 is less than equal to 3 and x2 will be greater than equal to 4. Accordingly, we have two sub problems, sub problem 1 and sub problem 2 as shown in this slide. The solution of these two sub problems can be obtained by following graphical method. The graph for the sub problem 1 shows that there exists no feasible region for the problem. Therefore, the sub problem 1 has no feasible solution, whereas for the sub problem 2 we have a feasible region and from the extreme points of the feasible region we find the optimal solution as x1 equal to 18 by 5 and x2 equal to 4 and the corresponding value minimum value of z equal to 132 by 5. Here again, since x1 is not an integer, so we will proceed further to make branch. We see that x1 star lies between 3 and 4. Therefore, the two branches will be x1 is less than equal to 3 and x1 is greater than equal to 4. Accordingly, we have another two sub problems, sub problem 3 and sub problem 4 as shown in this slide. Now, the optimal solutions for these two sub problems, sub problem 3 and sub problem 4, can be obtained graphically. The graphs are shown on this slide. For sub problem 3, we are getting a feasible region, whereas for the sub problem 4, we are getting an unbounded feasible region. But as we know, an unbounded feasible region not necessarily give unbounded solution. So, we may get a finite bounded solution. So, for the sub problem 3, we find the optimal solution as x1 equal to 3, x2 equal to 5, as this extreme point gives the minimum value z, which is equal to 27. And for the sub problem 4, that is the unbounded feasible region, gives the extreme point a44 and b46. The value of z at a equal to 28 and the value of z at the point b is equal to 34. Obviously, the extreme point a44 gives the optimal solution. Therefore, the optimal solution is x1 equal to 4 and x2 equal to 4 and the minimum value of z equal to 28. Hence, from these two sub problems, sub problem 3 and sub problem 4, we get the optimal integer solution of the given problem as x1 equal to 3 and x2 equal to 5, as it gives the minimum value of z, which is 27. We now discuss another programming problem called 0-1 programming problem. There are practical problems that can be structured only as integer programming problem, but some problems may consider only 0 and 1 integer values representing a yes or no choice and are known as 0-1 programming problem. The general integer programming methods such as branch and bound method can be used to solve a 0-1 programming problem simply by introducing one additional constraint that all the variables must be less than or equal to 1. We consider a practical problem, which is capital budgeting problem. In capital budgeting problem, we have to take the decision whether to invest or not to invest. Suppose that a firm has capital Ki to invest in year I, where I equal to 1 to up to m. There are n different projects that are competing for these funds. Suppose that the project J requires an investment of rupees kji in year I. Let Pj be the present value of all future returns from project J. A project may either be undertaken or not undertaken in a year. Therefore, our objective would be to maximize the sum of present values of all future projects within the capital constraint. To formulate this problem, let xj equal to 0 if the project j is not undertaken and xj equal to 1 if the project j is undertaken. Then we can formulate the problem as maximize z equal to p1 x1 plus p2 x2 plus pn xn, which represents the present value of all future projects subject to the constraint k1i x1 plus k2i x2 plus dot 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 kni xn, which is less than equal to ki for I equal to 1 to up to m, and xj is less than equal to 1, and of course, xj is greater than equal to 0 and integers for all j equal to 1 to up to n. In this module, we have discussed Gomory's cutting plane method for mixed integer programming problem. We have discussed branch and bound method, and finally, we have discussed 0-1 programming problem. In this problem, the variables are restricted to take only 0 and 1 values. There are many real problems in the world which can be formulated as 0-1 programming problem, such as capital budgeting problem, investment alternatives problem, and so on. With this comment, we end this module as well as this chapter.